Any questions? All right, let's pick up where we left off then. This was temperature in degrees Celsius, and this was energy in either calories or joules. Let's go to calories. And the numbers I had written up before, or I could just make up new numbers. Or perhaps I was picking an example that I already done.
The only numbers I got was 25 grams of water.
All right, so I have 25 grams of water. That starts out at negative 10 degrees Celsius. And when you get up to 115 degrees Celsius. It might be slightly different than what I've written on the board before. And based on my notes, it's like I'm working in joules here. So let's change this to joules. All right, so at each step, as I'm taking the water from negative 10 to 15, I'm putting energy into it. So the first thing I need to do is bring it up to its melting point. Once it gets to the melting point, I have to melt it. So this is melting. Now I've got liquid water at 0 degrees Celsius, and then I have to bring that up to its boiling point, or boiling point. And then I have to get it into gas form. Now I wrote vaporization, I guess vaporizing, melting, vaporizing, seems like they should be the same parts of speech at least. Now, specifically, vaporizing is a more general term. Boiling is specifically what's going on here. But vaporizing can happen at almost any temperature. But we're specifically taking it up to its boiling point, boiling it off. So parenthetically, right, boiling. And then I have to take it up that last bit up to 150 degrees. If I reverse the process, if I started with steam at 115 degrees and I want to get it down to an ice cube at negative 10 degrees Celsius, then it's the same process, just I'm removing energy instead of sticking it in. But I have 5 different sections here. I'll label this section 1, section 2, section 3, section 4, and section 5. And it's my understanding that, I know these are called Roman numerals, but I don't think the Romans actually used that symbol. I think that's the medieval times. All right, so we're going to do step by step. How much energy does it take to get the water into its new state? So, first off, I'm dealing with a change in temperature here in this phase 1. If I'm changing the temperature of an object, or in this case, 25 grams of ice, what formula do I use? And if you're not sure, Blue's is going to answer this without even knowing the question. Again. It's your chance to show off. Psychic connection. It's not today. All right. Since Luz cannot read my mind, what is the answer? The amount of energy it takes to change the temperature of a substance. No, not that one. It's Q equals, say it again? Yeah, MC delta T. So Q is equal to MC delta T. So M, the mass of what we're dealing with, and it's 25 grams. So, yeah, I think my specific heat is in terms of joules and grams. So 25 grams times the specific heat of ice, which I've written down as 2.05 joules per gram degree Celsius, times what is the change in temperature? Based on the board, pardon?
10.
Give me the whole thing.
10 degrees Celsius.
Yep. I'm taking it from -10 up to 0. That is a change of +10. And so there's the math problem, and that is 2.05. And that equals someone is going to share with us. Or hopefully 2 people will share with the same answer. Five 12.5. Okay. Units? Yes. So a little over 500 joules in order to get it up to, in order to melt it. All right, phase 2. Now I'm melting it. What is the formula for the amount of energy it takes in order to change the phase? More specifically, in order to change it from a solid into a liquid. It's another formula that starts with Q equals.
The first one, what is that formula is for what again?
What is this formula?
Yeah.
This is if I'm changing the temperature of a substance, it's the amount of energy it takes in order to change the temperature, given the mass of the object, the 25 grams, and what's known as the specific heat, which is a material dependent concept.
Is it Q equals MC?
Yeah, or the other, whatever I happen to use then. I'm gonna go with the L. There's 2 different latent heats. This is latent heat, mass times latent heat. What is latent heat of fusion or latent heat of vaporization?
Fusion. Fusion?
Yep. Even though we're unfusing, but it's still the same number, unless you want to squabble over plus or minus. And so the mass is 25 grams. And the latent heat of fusion for ice to water is written down somewhere here. There we go. 330 joules per gram. And then through the magic of fingers, toes, calculator.
8,250 joules.
8,250 joules. So it takes considerably more energy to melt it than it does to raise the temperature there. Questions up to here?
I didn't know where you got the 2.05 joules.
Per gram degree Celsius?
Yeah, was that a given?
That's a given.
Okay.
Yeah, it's the type thing on, if I'm talking about, that's specific to ice. So if I'm talking about ice, either I give it to you or, well, I'm gonna give it to you. It's either I give it to you in a problem or it's at the top of the page of formulas, or it's something that you just look up. I think on the master set, I give it to you, any of the information that you might need. All right, we're about to get into the next phases. Those are the two unique ones. Now it's just a matter of what's the substance and what's the temperature change. So we should be able to do this faster. So in phase 3, I'm taking liquid water, because I've now melted it. I'm trying to get it up to the boiling point so I can vaporize it. What is the formula that I'm going to use to figure out how much energy it takes to change the temperature of the water? Yep, it's the same one as we did in phase 1. Now C is different because the specific heat of water, liquid, and of ice are not the same, and steam is different also. So I still have 25 grams, I assume I haven't lost anything. Specific heat of liquid water, 4.1813 joules per gram degree Celsius. Times, what is my change in temperature?
100
The whole thing.
degrees Celsius.
Yep, that's it. And then the magic of Annapolis or Chisenbot, or however it's supposed to be pronounced. The answer is 10,453.25. Yep. So far, that's the most amount of energy. It takes more energy to raise it to 100 degrees Celsius, the liquid water at 100 degrees Celsius, than it does to melt it, which doesn't seem too bizarre. Phase 4. We now have this water at 100 degrees. It is not boiling. And we're gonna, so now we've got to stick energy in to get those molecules far enough apart to call it steam so that they will escape. Now, without special equipment, if I take liquid water, I will never get the water really above 100 degrees Celsius. Because once it does, gets to 100 degrees Celsius, it will turn to steam. Steam escapes, and what's left behind is still water that's at 100 degrees Celsius at most. So in the lab next week, we'll be playing around with this a little bit more. You should be able to get the water up to like 99 point something degrees Celsius or so. If the thermometer or temperature probe gets above that, above 100 degrees Celsius, then you probably don't have enough water in there. All right, so the formula that is to be used to get the water to boil, to turn into vapor.
Is it the N L, but with the D for vapor?
Yep. Q equals LLV. So we still have 25 grams because we haven't lost anything because we are that good. And then the latent heat of vaporization is 2,500 joules per gram. So 62,500. And then one last phase, we now have all this steam at 100 degrees Celsius, we now needed to get up to 115, yes, we need to. You will not feel as complete as a human being unless we finish that. What is the formula that we will use to deal with the change in temperature of the steam?
MC delta
Yep, say it with confidence, like you mean it.
T. MC delta T.
There we go. And of course, I left myself an incredible amount of space there. So it's gonna be 25 grams. I'll drop units because of space. Specific heat of steam is 2.08, very close to that of ice. 2.08 joules per gram degrees Celsius. I said I was gonna leave units off, so let's get back to that. 2.080 times the temperature change, which is 15. So somewhere just above 750.
780.
780. Let's see if I can draw that more standardly. All right. So we've now broken it up into parts, but we haven't actually answered the question. The original question is, how much energy does it take to take ice at negative 10 degrees Celsius all the way up to steam at 115 degrees Celsius? Now we gotta add. We're adding the amount of energy it takes for each step. And we have a grand total of I'm gonna guess it's bigger than 62,000. 72, 80. $80,000 change. What do we get?
82,495.75. Joules.
How many calories is that? So first off, we need to figure out how many joules there are in a calorie, or calories in a joule. What is that number? That's joules per calorie?
Yep.
So there's the math problem. So its essence, that's a 1 there. So we multiply the diagonal we know and divide by what's left over. So 82,495.75 divided by 4.184.
$19,716.
19,750.
16. 716.
700.
16.
All right, one more time.
19,000.
90,000. 19,000.
716.
16. Oh, we can say it down.
0.95. And a bunch more. 764.
Pardon?
Oh, you want the whole thing?
I'd like units.
Cal.
Yeah. All right, that's the number of calories. Those are science calories. That is not, well, that is physical science calories. That's not biology food calories. If we wanted to know the number of food calories, how many food calories is that? answer with great confidence. How many food calories, big C calories? Pardon?
Is it 1,000?
As a final answer? Or as a conversion?
That's the conversion.
Yes. What are you doing with that 1,000? You about to blurt it out with great confidence?
Maybe.
Okay.
Do you move the decimal point over 3 times to the left?
Yes.
Okay, then. 19.72 big C calories.
So if you could take a piece of ice at negative 10 degrees Celsius, keep it in your mouth long enough till it gets, or actually go through your body too, until you somehow convert it to steam, which is not gonna happen, but if you could burn off 19 calories, food calories. And then it'll give you an excuse to start eating candy to make up for the lost calories. Do you need an excuse to eat candy?